Okay, we're in the middle of doing the running coupling constant. We're really just doing the highlights of various steps about it. There's lots of little tidbits that are interesting. So let me just remind you where we were. What we did is we did the calculation of this diagram. We showed the important parts of it, plus the important part of that diagram was that it was zero. It vanished by dimensional regularization, though it's divergent in other regularizations. We ended up with pi AB alpha beta is I times 11 thirds Q alpha Q beta minus 19.6 odd numbers G alpha beta Q squared mu squared over minus Q squared to the epsilon over 2 times minus G squared over 16 pi squared C2 of the adjoint delta AB 1 over epsilon. Okay, C2 of the adjoint is just a fancy way of writing N, but we'll keep that notation because it actually, there's various identities that pop up in what we're doing next. Okay, this one, however, has to be completed by doing the ghost. So let's do the Ghost Lagrangian. The ghost term, again, there's a diagram that looks very similar, except that these ghosts run around there. So let's point out the interesting features here. So here we have pi AB alpha beta is, well, there's a minus sign from the fact that these guys are treated as fermions. Okay, and that's the piece that subtracts out the unphysical degrees of freedom. Then it's integral d4k, 2 pi to the fourth, I over minus I over k, no, it's plus I over k squared plus I epsilon plus I over k minus q squared plus I epsilon. So those are the propagators. And then the couplings, the Feynman rules say this is A, this is B, and let's make that C and D, F, A, C, D, and it's the outgoing momentum only. So it's a little bit odd. It's only the outgoing momentum, which I've called K alpha, and the other one is G, F, B, C, D, K minus Q, beta. So again, it's the outgoing momentum on that vertex also. Okay, the color factors are the same. This ends up giving us C2 of the adjoint. And there isn't too much else to report. This then comes into 1/3 Q alpha Q beta plus 1/6 G alpha beta Q squared times all the same factors. Okay, so I've pulled the same factors out. Let's not write them. The last interesting point here is that the sum is gauge invariant. Okay, so the sum is Q alpha minus g alpha beta q squared times the minus g squared over 8 pi squared 5 thirds c2 and 1 over epsilon dot dot dot. Okay, so that's a big deal. The fact that by adding the two you get something gauge invariant, it tells you that the ghost has been essential for that. Okay. This lets us pull out, so then we renormalize at q squared is minus mu squared, mu r squared, and we get z3 is 1 minus g squared over 8 pi squared mu over mu r squared to the epsilon 1 over epsilon minus 5 thirds c 2 adjoint plus 2 times the number of fermions over 3. That was from the fermion diagram that we did first. Okay, so that's the wave function renormalization. But in Yang-Mills, that's not the beta function. In QED, this was enough to pull out the running coupling, but it's not going to be here, and that's the less points of the next things I want to do. Okay. So, any questions up to that stage? Yeah.
Now, in the previous step, we had propagator, and it had no mass.
Yeah.
So would we have infrared divergence?
Not in this diagram. That's a good question. Let me just think about the structure. You know, the reason, what is the reason? Yeah, that's a great question. Q squared ends up regularizing, keeping it away from 0. So if I extend this out, it's k squared minus 2k dot q plus q squared. And there is a k and q up here also. But it doesn't blow up like 1 over q squared either. Okay, so I think in the place of the mass must be played by q squared. It's true in this diagram also here. What happens at low momentum in this diagram, you'll get logs of q squared over mu squared. So once you see one of the things, let's just do dimensional counting first. This is k to the fourth over k to the fourth times k squared. It equals something that goes like this by certainly the sum goes like that by gauge invariance. So the rest of this is going to be dimensionless. It depends on q squared and mu squared. So the only ratio that's possible is q squared over mu squared, and it depends on them like this to that power by dimensional arguments again. So it goes like log m squared over q squared. So that must be how the infrared stuff behaves. Okay, the vertex diagrams that we're about to do have infrared divergences, but we just chuck them away. Okay, I mean you deal with them separately. I mean right here we're not going to follow that part of it. Okay, so let's just talk a bit about the vertex function. Okay, we're going to show you the results from this. Remember this goes into the renormalization constant Z1 for a fermion. And in QED, we had E renormalized is Z1 to the minus 1, Z2 to the plus 1, Z3 to the 1/2, E0. So we absorb those features into the renormalized E. And Z1 came from the diagram that was like that. Z2 comes from wave function renormalization, which is that diagram. And in QED, there's this word identity, Z1 equals Z2. And we worked on this and we showed it from taking, if I take d by d p mu sigma of p, that was lambda of p, and p, the diagonal vertex function. So we worked that out. But that basically then says that this just goes over to Z3 to the 1/2, E0, they cancel out. Here in Yang-Mills, we have this diagram like before. We also have that diagram. Neither of these cancel by the same trick. The color factors are just different. So we want to take a look at that factor. So we have an extra diagram. Let's call this I. Call this double I. We have an extra diagram, and the color factors are going to be different, so we won't have the word identity working. And each of these will contribute. Okay? So let's look at the factors that are involved in this. I have minus Ig lambda mu of P and P prime. Well, I'll just write out the Feynman rule. It's minus Ig over 2 cubed integral d4k over 2 pi to the 4th minus Ig alpha beta over k squared plus I epsilon. So here's alpha, that's beta, or vice versa, I forget. It's actually the reverse the way I'm writing it. There's a gluon interaction here, which brings in a lambda b gamma. All right, I'll write it the way I wrote it here. So first I hit beta I have I over P slash minus K slash plus I epsilon, so that becomes K. This is P minus K. I have that gamma mu lambda A I over P prime slash minus K slash plus I epsilon. And then lambda B gamma alpha. So these lambda B's here are summed over, so that's this lambda and that lambda there. They're sandwiched around a lambda that's connected to the external vertex. So this is mu coming out here and color index A. Okay. The color factors are I have lambda B, lambda A, lambda B. So that's something that I calculated for you last time. We ended up showing that this was 4 times the Casimir for the adjoint. No, for the fundamental comes first. Minus 1/2 the Casimir for the adjoint. And you get lambda A back again. Okay, that's really the only interesting feature here to point out. The rest is like QED. It's the same calculation identically. I end up with then minus IG lambda A mu goes as, actually there is one more thing I want to point out. Minus IG gamma mu lambda A over 2, that's like the bare vertex. Then I get G squared over 8 pi squared, this C2 of the fundamental, minus 1/2 C2 of the adjoint. I've got my mu squared over, let's call it minus P squared, to the epsilon over 2, 1 over epsilon plus dot dot dot. Okay, so the other thing that's worth pointing out here is that we're going to renormalize this at some P squared equals minus mu R squared. So we're just going to take some P squared. So this is off shell. And that's a good thing, and the reason you do it here, it's a good thing to do. The reason you do it is you don't want any mass dependence. So it's good to use a mass independent renormalization scheme. And that's what so this is mass independent renormalization scheme. Is the phrase that you use. And that's important because some of this is going to go into the running coupling constant. You don't want the running coupling constant definition to depend on the mass of one of the external lines, because then you'd have to change it every time you change an external line. Okay? So that's that piece. Okay, the other one, let's do the other one. So the other diagram hooks up to the gluon lines. It's more complicated. I won't write the whole thing. Lambda A mu. Well, there's an g cubed integral d4k, the usual factors. The interesting feature here is again the color scheme. There's a gamma, so here's some index alpha. I'll use the propagator being diagonal, so that becomes alpha. This is beta, that's beta, and this is mu and A. Again, external. Okay. So there's lambda c over 2 at the fermion line. There's one fermion propagator, k slash minus m. The other fermion line is gamma alpha. Yeah, actually, so one of these is beta. Let's make that one beta. Lambda b over 2. The triple gluon coupling comes proportional to F, A, B, C. And then there's some numerator factor here, which is a function of mu, alpha, and beta. And I get P minus K squared and P prime minus K squared. The gluon propagators. And there's nothing too interesting about n mu alpha beta except that it starts off linear in K. So it starts off, for example, 2k mu g alpha beta minus g mu alpha k beta minus g mu beta k alpha. Okay, yes. Plus dot dot dot. Okay, that actually is the fact that there's a linear piece actually helps because there's these gamma factors here. We end up having to get a gamma mu coming out at the end, and that comes from the k alpha piece here and the k piece in the n, and that's uniquely the place where you get that from. That's the most divergent piece. Okay, so aside from that little bit, the color factors are the important. We have F, A, B, C, lambda C, lambda B, and we have to evaluate that now. That's not one we did before, but it's not that hard to do because F is antisymmetric. This is F, A, B, C. It's put a factor of a half and turn this into the commutator because it's antisymmetric, which is then 1/2 times F A B C F C B D times 2I lambda D, which is minus it becomes plus C2 the adjoint lambda A. So this combination turns back into just lambda A, one factor of lambda A with a C2 of the adjoint. And then after some calculation, you get minus I G lambda A mu is, there's a minus I G lambda A over 2. We just calculated that part. There's a gamma mu. That's a little harder to get, but this, again, the mu index was sitting up here, and you've got 3 gamma matrices here. There's a gamma there, a gamma from K slash, and a gamma there. But you can see how it comes out here, for example, in the G alpha beta piece, K mu. The G alpha beta gives me a factor of 1 K slash is left there, so minus 2 is the overall factor. And then the K slash times K mu when integrated turns into K mu. Okay, sorry if you don't see it, it's okay. But then I end up with G squared over 8 pi squared 3 halves C2 adjoint 1 over epsilon plus dot dot dot. Okay, and if you combine these, Z1 for fermion turns into 1 minus C2 of the fundamental plus C2 of the adjoint now let's see, I want G squared over 8 pi squared mu over mu r to the epsilon times 1 over epsilon plus dot dot dot. Okay, so the p squared is turned into mu r squared, the renormalization point, and we're taking that, the same renormalization point as we take the gluon wave function renormalization. Last bit is we have to do wave function renormalization. Let's not write out everything here. Just point out that this is proportional to, there's a lambda a there, a lambda a there. The color factor is lambda a over 2, lambda a over 2, which turns into C2 of the fundamental times the unit matrix. So this guy only involves C2 of the fundamental, and so Z2 for a fermion turns into 1 minus C, the Casimir for the fundamental, G squared over 8 pi squared mu over mu r to the epsilon 1 over epsilon. Okay. So at this stage it's worth looking at this. Does Z1 equal Z2 like in QED? You see that one of the pieces does work that way. The C2 of the fundamental is that way. So that's going to end up dropping out of the calculation. The end result will not depend on this Casimir. It will still depend on that. We'll still have a piece left over from that. And just to look ahead, that piece came out of both of the other calculations. It came out of the fermion side, and it came out of the gluon side. So I'll piece those together in a minute. Okay, so let's combine everything. Okay, so we have G. Remember, we're doing renormalization using this diagram. We have, this goes like g squared, so g is the square root of that. If you want, there's a z1 minus 1 from up there. There's a z1 minus 1 down here. There's a z3 in there, and there's z2 to the 1/2 from each of the external fermions to the 4th. Okay, the end product is that it ends up being z1 for a fermion minus 1, z2, z3 to the 1/2, g3, or g0. Okay, so we have those renormalization constants to multiply the bare one by to get the renormalized one. This gives us twice that, or that thing squared. Okay, so in order, let 1 over epsilon hat equals this g squared over 8 pi squared mu r squared to epsilon over 2, 1 over epsilon. So in order, these guys are 1 plus C2 fundamental plus C2 adjoint 1 over epsilon hat 1 minus C2 fundamental 1 over epsilon hat times 1 minus 1/2 minus 5/3 C2 adjoint plus 2 times the 2/3 number of flavors, number of fermions, 1 over epsilon hat G0 adds up to 1 minus 1/2 minus 11/3 C2 adjoint plus 2/3 number of flavors number of fermions there. So there's our overall renormalization. Fans of our book, I have to admit we have a correction, which I just found in preparing these notes, is if you look in the book, you see C2 fundamental sitting there. There's a major typo. I'm sorry about it. The number works out right, but it's not C2 fundamental. That has canceled out. So there's a couple typos associated with that. If you want to see how to correct your book, you can come. I think we have a new version corrected. Okay, so I only caught that working through this, and nobody has pointed it out to us. I'm surprised. Okay. But then, since 1 over epsilon hat, remember you can see the definition up there, it looks like is g squared over 8 pi squared 1 over epsilon plus log mu over mu renormalized. Then if I take the renormalization point dependence of 1 over epsilon hat, that's minus g squared over 8 pi squared. We then end up with the renormalization point dependence of G renormalized equals, well, it turns into minus G cubed over 16 pi squared 11/3 C2 adjoint minus 2/3 the number of fermions and that guy's just n. That's the beta function of G, and that's our, this is the famous minus sign that gives you asymptotic freedom. There's a minus sign that comes, that sits from the fermion piece, sits here, gets is positive. Actually, let's break that down a little bit more. It's actually interesting that where does that 11/3 come from? So of the 11/3 n factor, we get from this diagram and this diagram, that's the ghost, we get 5/3 n. Okay, so some of it comes from there. However, it also comes from, there's some stuff that comes from here, that diagram, and there's some stuff that comes from that diagram. This one is minus 3/3 n. Of course, clearly that's 1, but just to put it in the same units. And this one is 9/3 n, so I get 6/3 n from the total of those. So actually the biggest factor is, in this one, this way of calculating it, is not the vacuum polarization, which, well, I mean, that's not so bad, but it's the triple gluon coupling. But no matter what the case is, the fermion piece, so all the fermion pieces are negative. Goes to an overall plus sign. The gluon pieces, all the gluon pieces, or all the, gauge bosons, go to negative pieces. Okay. So that's that. Okay, any questions about the decomposition here? Now clearly, if you go through a different pathway, so there are these various ways of defining renormalized charge. You could do it with purely a gluonic vertex, in which case there's no fermions around, except in the vacuum polarization. Things then work out different in the different decomposition. But it's interesting here that you always need these vertex functions. It's never just the vacuum polarization. And it makes it, in fact, a major contribution. Okay. All right, so let's go from there to this running coupling. Okay, we have mu r dg d mu r is minus b0 of g cubed. And b0 is this 1 over 16 pi squared 11/3 n minus 2/3 the number of fermions. And let's just quickly run through the steps to get the final form. We integrate this Let's integrate it dg over g cubed from, let's call it g1 up to g of, I'll call it g of q squared, just the upper endpoint. I'll just give it that name. That's minus b0, the integral d mu r from mu1 up to q, just again, just the name at this stage. So I end up with then minus 1 over g squared of q squared plus, and there's a 2, plus 1 over 2 g squared of mu1 squared equals minus b0 log q over mu1. Okay. We now define 1 over g squared mu1 squared is defined to be 2b0 log mu1 over lambda for some lambda. Okay, this is just a definition of lambda, but this is some number. Mu1 is fixed. Lambda is adjusted to make that number work out. Okay, when you do that, then we get 1 over g squared of q squared equals 1 over g squared of mu1 squared plus 2b0 log q over mu1. The mu1s cancel out, and this becomes b0 log q squared over lambda squared, so that then g squared of q squared is 1 over b0 log q squared over lambda squared, and alpha n q squared g squared over 4 pi is then 12 pi over 11n minus 2 times the number of fermions log of q squared over lambda squared. Okay, there's your classic running coupling constant that falls like 1 over log q squared. So q squared gets bigger, alpha gets smaller. Okay. Any questions about the whole combination that went into that? Okay. If there's not, I want to do a few what I call QCD issues on how to use this. So in QCD, n is 3, of course, but then I want to do 3 things. I want to do matching these. I want to talk about scheme dependence. And higher order. Okay, so these are three features that can be sometimes a bit subtle about applying this. So first, we call it matching, but it's basically the question of NF equals what? What should you use? The physics here is that the formulas that I've gotten imply that Q squared is bigger than the mass of a fermion. So, for example, we have pi of Q squared goes like Q squared over M squared for Q squared less than M squared, but it goes like log Q squared over mu squared for Q squared much bigger than M squared. So the rule here is that you only use quarks lighter than the scale that you're working at. So if you're defining alpha 3 at the Z mass, you use NF equals to 5. Alpha 3 at the LHC will be NF equals to 6. And if you're working at lower energies, alpha F4 GeV is NF of 4. And so the trick is, how do you do that? And that's what I call matching. At the various points, if you're at the LHC, you have this factor is 33 minus 2 times 6. Okay, so there's the factor 33 minus 2 times 6 is 21. At the Z, the same thing as 2 times 5 is 23. And at 4 GeV, 2 times 4 is 25. The trick is that you have to have this alpha S, alpha 3 has to be of Q squared has to be treated as continuous. So as you run it down, you have some running let's exaggerate, they're slightly flatter there. When you hit the top quark, it runs slightly faster. And then when you hit the B quark, exaggerate, it runs faster. So the speed which it runs changes, but the value of the function across there has to be a constant. So you have to, for example, match alpha S at MB is, well, it's 12 pi. If I was treating it from above, it would be 23 log MB squared over, let's call it lambda 5 squared. This is from above. It's also then treated from below, it's 25 log, so it's 12 pi over 25 MB squared lambda 4 for those to be continuous, you have to use different lambdas in different regimes. So if you end up working it out, it's mb squared over lambda 4 squared is mb over lambda 5 squared to the 23 over 25. Okay, that ends up giving you continuity. So there's no such thing as lambda QCD. You have to specify which region you're using it in, and its actual value changes. So you have to be, people tend to be cavalier about this and just talk about lambda QCD, but in fact its value changes not insignificantly as you go from one region to another. Okay? The second thing I wanted to talk about was scheme dependence. Okay. This comes when you try to put a number on lambda QCD. And you know that there can be different renormalization schemes. So examples of different schemes are the minimal subtraction scheme, MS. You'd have GMS squared is 1 minus B0 G squared over 16 pi squared 1 over epsilon G, I don't want that square, take the square away, G0. Okay, so you, in this case, you only absorb the 1 over epsilon piece. In the MS bar scheme, the relation would be GMS bar equals 1 minus B0 G squared over 16 pi squared 1 over epsilon minus 1/2 plus 1/2 log 4 pi minus gamma over 2 G0. Okay, so in MS bar, one carries along these extra factors log 4 pi and gamma over 2 that always come along in a calculation. Gamma is this Euler constant. And so these numbers, if you define them and measure them, they have to be different. In particular, GMS bar is GMS 1 minus GMS squared over 32 pi squared log 4 pi minus gamma. So they're different numbers. So that this tells you that you have to then even specify the scheme. Lambda MS bar is not equal to lambda MS. They can't be the same number. So you're then required to tell us both the scheme and the number of fermions that you're working with. However, the difference between these guys is higher order. So this is equivalent Okay, so you can sort of see this if I have alpha ms bar of q squared. This is this number, it's 4 pi over b0 log q squared over lambda ms bar squared. If I write this as b0 log q squared over lambda ms, no bar, squared, times a factor 1 plus some correction factor. So this is the difference. You can then expand that. This turns into alpha s and alpha minimal subtraction, and if I did the expansion right, it turns into minus log 1 plus a over b0 log q squared over lambda ms quantity squared. So this is higher order. And in fact, the way you would actually calculate this is you'd go back up to this relation up here, and you can see that the relation is going to be higher order, and so that you can get this factor out just from doing that. Okay, so the running coupling constant in lambda is not perfectly well defined at leading order. You really need to define it precisely. You need to go to next order. Okay, and then the last thing I like to do on the beta function is show you what happens at next order. Okay, since you really need the next order to define it, the beta function clearly then starts off as mu dg d mu. Well, we had minus b0 g cubed, and there could be some b1 g to the fifth. The next one will be a power of g squared higher because you do an extra loop. So this comes from 2 loops. Okay. If we solve this, we have the integral mu1 up to q b0 I'll take out a factor of b0. Let's write it as d mu r over mu r. That's one side. I'll pull the minus sign there. Is the integral dg g cubed plus b1 over b0 g to the fifth. Okay, so I have to do that integral. If I'm going to let x equals to g squared, this is 1/2 the integral dx x squared 1 plus b 1 over b0 x, which, since we're doing this perturbatively, I could just write as 1/2 the integral dx 1 over x squared minus b1 over b0 1 over x. Okay, so I expand this. 1 minus something of x. 1 over x squared is the 1. 1 over x is the the second one. This turns into then 1 over, well, it's just 1 over x minus 1 over x1 minus b1 over, so it's over here is 2b0 log q over mu r. It's 1 over x, and then I have b0 log x. All right. What I wanted to get is that log piece there. So the next piece in this expansion goes like log x. Remember, x is q squared, is g squared. So this is 1 over g squared. Here's g squared. So we then do the solution as before. We define some constant. The actual definition is actually something that goes like 1 over x1 plus b1 over b0 log x1 is b0 log lambda squared. So you pull a piece of that in, do a bunch of algebra, and you end up with g squared is the following. You get g squared is 1 over b0 log q squared over lambda squared as before, but then when I invert, I get also 1 plus b1 over b0 log g squared. I'm doing this perturbatively over divided by log q squared over lambda squared. So it's roughly 1 over b0 log q squared over lambda squared 1 minus b 1 over b0 squared log q squared over lambda squared over log q squared over lambda squared. All right. What I've been doing is I have log of q squared here. I'm replacing that by the lowest order, which goes like log 1 over log q squared over lambda squared. So the correction piece is log log. And I'll just give you the real answer in QCD. In QCD, the next order piece is we have alpha s of q squared. The leading piece was this 1 over 12 pi 33 minus 2 number of flavors log q squared over lambda squared. The next order piece was 1 minus 6 times 153 minus 19 times the number of flavors over 33 minus 2 number of flavors squared log of log q squared over lambda squared divided by log of q squared over lambda squared. Okay? So the numerical factors I'm not that interested in, but the correction being log of log is the interesting feature, and that comes straightforwardly from just doing this integration g squared plus g to the 5th with some coefficients chug that in, do our definitions, and you end up with log-log. All right. So that's where we're going to end the running coupling constants. Okay. I want to come back and I want to, my last thing, I'll take questions here, but as I'm going to do one calculation in full detail, which I skipped over so much last time, I'm going to do the calculation of the magnetic moment of the electron in showing you the features, showing you the way through, because we've really not done much explicit loop calculation. So let's do one explicit loop calculation again. I mean, we did vacuum polarization. We'll do this guy. It's probably the most famous calculation. We'll work it out next time, and then we'll move on from gauge theory to effective field theory. Okay? Any questions about this, where we're going, what we're doing? All right, let's stop there then. We're a few minutes early, but since I have one calculation to do, let's save it for next time.